Hello everyone and welcome back to our Python data science workshop. I'm Chi, your old friend, and it's so happy to see you here again. I'm very excited today because we are diving into Geopandas, a very powerful tool for working with geographic data in Python. So look at this stunning image of Earth at night or nighttime light. It is a perfect example of the kind of geographic data that we'll learn to analyze. So let's start with why this matters. So when we talk about challenges like climate change and public health, we're dealing with two crucial types of data. So human and environment. These aren't just random numbers. They're tied to specific locations on Earth, and that's what makes them geospatial in nature. Now, traditionally, we would use GIS, which stands for Geoinformation Systems, to work with this kind of data. But there's a catch. While GIS platforms are great for visualization, they can be challenging for reproducible analysis and processing large datasets. Plus, they often work kind of like a black box, meaning we don't really know what the actual data processing is. And this is where Geopandas comes in. And if you are familiar with pandas already, you'll find this transition quite natural. Geopandas actually builds upon pandas, NumPy, and other common Python packages. It essentially extends pandas' capability to handle geographic data. And in other words, Geopandas enables a pandas series data frame to have a spatial dimension, which is taken to a shapefile in a GIS platform. And importantly, Geopandas can perform geometric operation. But before directly jumping to the practice of Geopandas, let's first do a quick geospatial 101 to get familiar with some of the basics about geospatial data. So now looking at this diagram here, we can see that geospatial data comes in two main types. That is vector and raster. So vector data can be points, line, and polygons. So point like a city location, line like a road or river, or polygons like a lake or building footprint. Well, on the other hand, raster data, they are shown in the grid below, and it is organized more like a matrix of cells, and each grid would contain a specific value. And what makes GeoPandas particularly useful is how it handles the spatial data. It takes the standard pandas data frame and adds a special geometry column using the shapely objects. And this allows you to perform geometric operations while retaining all the functionality as a regular pandas data frame. So let's put what we have talked into practice. And we'll start with a simple pandas data frame that contains some basic location data. And as you can see here, we're creating a data frame with three columns, location, names like P1 to P7, and data 1 and data 2, these two columns. So once we created this data frame, we can see that it's printed. And at this point, while we have data associated with locations, our data frame doesn't actually know where these locations are in space. And to make this data geospatial, we'll need to add coordinates. And typically this will be latitude and longitude. But for this example, we'll just use simple x and y coordinates. So now we're adding two more columns, x and y, which will be their locations in an imaginary space. And each pair of the coordinates will tell us exactly where each point should be located on our map. And now, after we have the x and y column, here comes the interesting part. So to convert our regular data frame into a geodata frame, we need to create a special geometry column, and we do this using the shapely points objects, which will combine each x and y coordinates pair into a single geometry point. And notice that here we're using a list comprehension with zip to create this point efficiently. So what this will do is that we're using the shapely point module, and then we just zip them into a point vector and And then using the geopandas.geodataFrame function, this will convert them into the geometry column. So if we now look at the output, we now have all our original data plus the coordinate columns. And what we see that here is that we have a geometry column that contains our shapely points. So you can see that these are point data sets. And we can check the type of the geometry for the first row, and we can see that it is indeed a geometry point. So one of the powerful features of Geopandas is its plotting capability. Using the plot function, we can easily visualize our point on the coordinate plane. And the interesting thing here is that we can use our data values to control how the points are displayed. So for example, here we're plotting the data 1 column, but if we want to also plot data 2, we can just copy this code and then change it to data 2 column. And as we can see that now the legend bar has also changed, and now we have the data 2 also plotted. And this is just a basic example, but it shows the fundamental workflow. Start with your data, add spatial information, convert them to geometric objects, and then visualize or analyze as needed. Now, let's apply what we have learned to some real-world data. And again, we'll be working with the Ghana DHS data from 2014, which contains information about household across Ghana. First, we load our CSV file using pandas, and we can see that our dataset already has the geographic coordinates as we need. So if we go back to the last two columns, we can see that we have a column called lat and a column called long, and this stands for latitude and longitude. And similarly, we can create our geometric points. Notice that we are using the same approach as before, but now with real geographic coordinates, longitude and latitude, instead of the simple x and y values. And the order here is important when creating points. We always first put the longitude first and then the latitude. And next, here it comes, and then we convert this again to a Geopandas data frame. And then next comes a very crucial step that we didn't do in our previous example, that is setting the coordinate reference systems, or CRS. Here we are using the EPSG 4326, which is the standard geographic coordinate system used by GPS devices and web maps. And this step is essential if we want to properly align our geodata frame. We can see all our survey now as associated geographic points. And now in the end, you can see that it's converted into geometry points. And if we print this, we can see that the geometry column has paired all the latitude and longitude coordinates into the point objects. And now we can see that our table has been already geospatialized. And to visualize this data, we can use the Geopandas plotting function, which provides a nice interface to Matplotlib. So we'll create a simple plot showing the geographic distribution of our survey response. So first, we can import the Matplotlib, and then we create a figure, and then we just use the plot function, and we set the color to be gray, the marker size to be 5, and then it will be plotted on the X that we created also. And just put some label and title, and now we can see that all the dot or the location of the surveyed household has been plotted in this simple map. And what's more interesting is that we can even make our visualization more informative by incorporating some of the actual survey data. So instead of showing all the points in same color, we can visualize the rural-urban distribution of our surveyed locations. Here, we can see that we add the column equals to rural-urban argument, and also we specify the legend location, and we plot this, we can see that the rural is dark blue and urban is light blue. So it gives us a better understanding of our data sets. So this is a simple example, but the same approach can be used to visualize other survey variables like the wealth index, health indicators, or any other categorical or numerical data in our dataset. And this kind of visualization helps us understand both the geographic and demographic patterns in our survey data. And now going further, let's explore another important aspect of Geopandas, that is working with shapefile. So Geopandas can handle various geospatial file formats, including shapefile, also CSV, also JSON file, and shapefiles are particularly important as they are a standard format for storing geographic vector data. And for this example, we'll work with a shapefile that contains something quite interesting. So it has the boundary of every country or region on the planet. And before we can use this file, we need to first set up our file path correctly. And in Python, we typically use the OS module to handle file paths in a way that works across different operating systems. And once we specify the file size or the file paths, then let's import them as a Geopandas data frame. And now we've printed the first 5 rows of these data sets. And as you can see, it has tons of columns, and it has some basic characteristics for each country. For example, the admin, their name in different languages. And again, when we look at this geo data frame, you'll notice it looks very similar to a regular pandas data frame. It has the familiar tabular structure with rows and columns. And however, the only key difference, as we can see here, is that in the very end of the column, we can see the geometry column. And this special column contains shapely objects that represent the geographic features for each country. And what's particularly useful is that Geopandas data frame maintain most of the functionality you're already familiar with from pandas. And you can use the same method and attributes like head or dot columns and other data frame operations. And this means that you can leverage your existing pandas knowledge while working with geospatial data. So for example, if we want to check the types and also all the columns, we can see that it is a Geopandas geodata frame, and also we have an extensive list of the columns here. And also we can check the shape of our Geopandas data frame. We can see that we have in total 254 columns or rows and 95 columns. And you can also sort the pandas table by variables that you select. For example, we can sort the rows by population estimate for each country in a descending order. And then you can see that pandas data frame has been sorted. And the number 1 populous country is China, followed by India, and then the United States. And you can also subset the columns and also the rows, and this is similar to what we did with pandas before. And here we're only showing the country names and population for the top 10 most population countries. And so this is the list of the top 10 most populated countries. Now, let's put our geographic data to work by creating a visualization of global GDP per capita. So first, we'll need to create this matrix by combining our GDP and population data using a simple arithmetic operations, just like what we did in regular pandas. So from this list, we can see that it has a bunch of different indicators, and from this table, we can see that it has the GDP per year and also population count. So now we're creating a new column named GDP per capita, which is the division of GDP per country and also by the population, and multiply by 1 million to get the per capita values in the standard unit. And looking at the first few values using head function, we can already confirm that our calculation worked correctly. And notice that within just like 5 countries, how the GDP actually varies significantly, ranging from 7,000 to nearly 27,000. And now, for our visualization, Geopandas give us two approach. So the quickest way is to simply use the gdf.plot function with our new GDP per capita column, and this gives us a basic choroplast map where each country is colored based on GDP per capita. While this is useful for a quick look, we might want more control over how our maps appear, because now we can see that the legend bar is too big, and also we cannot really see a pattern from the map. So for a more refined visualization, we can use the matplotlib function, and this allows us to customize every aspect of our map. First, we can set specific parameters like the figure size and adjust the scale using the V minimum and also the V maximum to better represent the data range. And notice how we set the minimum value to 300 and the maximum value to 100,000 to create a more meaningful color distribution. Because the thing is that the GDP might vary super significantly across different countries. And if we plot this map, and also we put a shrink function to shrink on the legend size. And now we can see that the resulting map tells a much clearer story about the global economic disparity. So the darker colors represent lower GDP per capita, as you can see from the legend. And while the lighter colors, the lighter blue, shows higher values. And you can clearly see that patterns like the higher GDP per capita are concentrated mostly in Western Europe and North America and Australia, while the lower values are largely found in many parts of Asia and Africa. And we have also added proper labels and a title, and by using the plot type layout function to ensure everything fits nicely in the plot, including the legend. So this kind of visualization helps us quickly understand the global distribution of economic output within just a few line of codes. So now on your own, I want you to modify the code that we just had before and to make a choroplast map for population rank for only Africa. And there's a hint that you will need to subset the data on the continent level. So you can try to find the column that corresponds to the continent. So now let's talk about a common scenario in geographic data analysis, that is combining tabular data with spatial information. And this is something you'll encounter frequently when working with real-world data, as geographic information often comes from different sources than your analytical data. And for example, you may have a dataset with column called country, but it does not have a geographic boundary for the country. And then you will then have to merge the dataset with a second dataset that has the geographic boundaries. And this is often the case where the CSV file you want to attach to a shapefile to make a map. To merge dataset, we can use the pd.merge function. And for this, we're going to use another CSV file which contains multi-year DHS survey data aggregated at country level. So the first thing to do is to load our dataset. So after loading our dataset, by checking the first 5 rows, we can see that we have the DHS indicators aggregated at country level, and it's a multi-year dataset, so across from 2008 to 2010 even. And we can see that our dataset has a column named country, which is the first one, and this has a categorical geographic information that we can likely use to concatenate to our geometry data from the word countries.shapefile. But first, we need to look at what the columns we need from our word countries shapefile. So again, if we check all the columns in our geo data frame, and we can see that we have a large number of columns. And what we need to do is that we need to subset them to only keep the essential columns, which is the country names and their geometric information. And this will help keep our data clean and focused. So Now let's create a subset of our geodata frame which only contains the name columns and also the geometry column, and don't forget to add the copy function. And now if we print ahead, we can see that we have the name and also their geometry. And before we can merge the two datasets, here is an important detail. That is, the column names in both datasets must match exactly for the merge function to work. And in our case, we need to rename the name field to country to match our survey data earlier here, country. So we can use this code to rename our columns by passing a dictionary name converted to country and in place equal to true. And now we can see that our GDF underscore sub has been updated. The column name has changed to country. And now we just use the pd.merge function as we learned before. Here we're doing an inner join. We're attaching the GDF geometry columns to the DF columns using the country column as a key. And now if we check the columns of our DHS DF underscore M, we can see that the final column is the geometry column, which means that the merge has been successfully done. But there's a catch. So after merging, we can see that our geodata frame is converted back to a regular pandas data frame. And this happens because pandas doesn't know about the geometry types. And to fix this, we'll again need to convert our merged data frame back into a geodata frame. And Geopandas is smart enough to look for the geometry column and handles the conversion automatically. So we just need to use the gpd.geodataFrame function to convert our data frame from a regular pandas data frame to a geodata frame. And now we can see that the class has indeed been changed. And now here comes a little exercise. You can pause the video and using the georeference and using the Geopandas data frame that we just created to plot the stunting rates for different countries in 2015. Okay, finally, let's talk a bit about one of the most fundamental concepts in geographic data. That is coordinate system and spatial projection. And this might sound a bit technical, but it addresses a basic challenge. How do we represent our spherical Earth on a flat surface? So if we look at the diagram here, it shows three main ways that cartographers have developed to project the Earth onto a 2D surface. So we have cylindrical projections where you can imagine wrapping the Earth in a cylinder and unrolling it. And we also have conical projections which use a cone shape, and as well as planar projection which project directly onto a flat surface. Each of these methods serve different purposes and comes with its own trade-offs. But now in the world of digital mapping, we use what we call CRS to keep track of how our geographic data is projected. And you can think of this as a set of instructions that tells our computer exactly how to convert locations on our round Earth into coordinates on a flat map. And in this tutorial, a full overview of geographic projections and coordinate system is out of the scope, but you can click this hyperlink and to get yourself more familiar with these terms and the basic scientific method behind it. But for this class, something crucial to remember is that first, whenever you're working with multiple geographic data sets, you must always check the CRS of your data to make sure that two or more data sets are in the same CRS and the projection before you perform analysis. And also, second thing is that sometimes if they're not in the same projection or coordinate system, you may need to reproject your data. However, reproject data will fundamentally alter the data by itself, and this is okay, but it will add some spatial uncertainty to analysis, and we'll talk more about this later. Well, one thing cool to know is that one of the most common standardized global or web mapping CRS is the EPSG 4326, which is the World Geodesic System 9084. And if you want to check your data's current CRS, you can use the .crs attributes. And we can see that the coordinate system is WGS84. And if you want to check what kind of methods or attributes you can apply or your CRS has, you can run this and you can see that there are so many different functions or methods that you can do with the CRS. And if you plot the data, this is a WGS84. It's a flat projection and they are all projected in a 2D surface. Well, to reproject your data, for example, if you want to reproject into a different CRS, here you can use the function 2_CRS, and then you can put name or the code for the CRS. And if we run this and plot it, we can change that. It changed from a flat surface to a more of an oval or like rounded shape. And this projection, it distorts the edges of the Earth and produce more an oval map. In essence, all projections distort one or more of the follows, like area, direction, shape, and area. But some do a better job for preserving this information than others. And it is really context dependent on what type of CRS you want to choose. For global, we usually use the WGS 9084. So in the end, after we have finished our data merging from the CSV to our shapefile, how to actually export our merged Geopandas data frame to an S3 shapefile, it is quite straightforward in the Geopandas. So first, you want to check the CRS to make sure that it is on the right coordinate system that you want, and then you can specify the file path. And in this case, we're saving it to the data folder. And once you specify the file path, you can use the function of gdf.toFile function to export your Geopandas data frame. And the export file can be either an S3 shapefile or it can be also a GeoJSON or even CSV. And the only thing you need to do is that you need to specify the driver, and in this case, since we are exporting it as a shapefile, we select the drivers to be S3 shapefile. And here we get a warning saying that we have some column names longer than 10 characters, but so it will be truncated, but still it is fine as long as we understand what the warnings mean. And now we can see that we have our shapefile exported to the data folder that we just specified. And that's all for today. I hope you enjoyed today's session and feel free to dive into any of these functions and happy coding.